Hello everyone, my name is Jan and I represent MeshSplatting, Differentiable Rendering with Opaque Meshes. In 2023, a new technology has arrived that conquered the world of 3D reconstruction, Gaussian Splatting. Gaussian Splatting reconstructs the world with millions of tiny small 3D blobs or 3D Gaussians that can be squeezed, made larger, which can change the position, the color, the opacity, and by doing so, we achieve high visual quality while still being able to render in real time and to train in under 30 minutes. However, 3D Gaussian Splatting also has some limitations. The color of each pixel is not obtained by a single Gaussian, but it is the accumulation of multiple Gaussians. Therefore, to get the color of a single pixel, we have to iterate over hundreds of Gaussians and accumulate the color until we obtain the final color of the pixel. As a consequence, we cannot take advantage of all the techniques in computer graphics, such as function cutting, and therefore rendering is not really efficient. Also, for many other downstream applications, Gaussian Splatting has limitations. For example, for gaming. As each Gaussian is semi-transparent, there is not really a surface, and therefore we cannot do physics or collision handling. Also, for VR and AR headsets, as we have to iterate over multiple Gaussians to get the final color, devices with low computer power, they cannot render at a really high speed, and therefore the user will not have a smooth experience with headsets. Also in physical simulation, as the world is just represented by millions of Gaussians to visually be good looking, however, they don't have a physical meaning in Gaussians. However, there is one representation that can do everything, and that's the mesh. So can we just transform the 3D Gaussian representation into a mesh? And yes, you can, but you will lose a lot of visual quality. For example, you can see that the chair, the tiny structures of this chair are just getting removed by meshing the Gaussian representation, and also the visual quality just increases. Another limitation is that it's much slower, because we first have to train the 3D Gaussian representation, and then we have to apply some post-processing to just extract the mesh from the Gaussian representation. So overall, it's just worse quality, it's slower, and it has just many limitations. A much better representation is already triangle splatting. In triangle splatting, we replace the Gaussian by the most fundamental primitive used in computer graphics, the triangle. However, also in triangle splatting, we still have a couple of limitations. For example, the triangle is still semi-transparent, which means we still have to iterate over multiple triangles until we get the final color for a pixel. And also triangle splatting is a triangle soup, which means that the triangles are not connected with each other, and we just have a triangle soup. So what if we can directly optimize a mesh? That's exactly what we did in MeshSplatting, where we optimize end-to-end a mesh, which can, after training, immediately be used for downstream applications without any additional post-processing steps. So the first step that we had to do after triangle splatting was to find a way to connect triangles. In triangle splatting, each triangle is defined individually, which means that there's no possibility to connect triangles. In MeshSplatting, we define a set or a large list of vertices, and all parameters are stored per vertex and not per triangle. And each triangle is then simply defined by the 3 indices of the 3 vertices that define it. And then we can simply connect triangles by just using the same vertex. And then the gradient is simply the accumulation of all the triangles that are connected to that given vertex. Then the second challenge is how can we actually optimize a mesh? Because a mesh is just a discrete triangle, and if you have a discrete triangle and we rasterize towards the camera viewpoint and we want to calculate the loss, there will just be no gradient as a triangle is discrete. And if there's no gradient, there's no optimization, there's no learning, and eventually we do not end up with a high quality reconstruction. So what we do is we first start with a soft version of the triangle, which you can see here at the bottom of the image, which is just a smooth transition from fully influenced to a pixel to no influence to a pixel. And you can see that initially at the beginning of the training, we start with the soft version of the triangle, and then over training we converge towards a fully opaque, solid triangle. So how do we now end up with or form the set of images to the final mesh? So exactly as in 3D Gaussian Splatting, we first take a set of images, we run it through CodeMap to get the parameters of the camera and to get an initial point cloud. From this point cloud, or for each point in the point cloud, we then initialize a single unconnected triangle. So that looks like this. So at the first iteration, we just have a set of unconnected triangles. Then for the first 11,000 iterations, we just optimize this triangle soup. At the top right, you can see how the average triangle looks like in the scene, and you can see that initially it's this smooth, semi-transparent triangle. After 11,000 iterations, we already then have a first optimization or reconstruction that looks quite good, but it's still a triangle soup. So we have to now connect the triangles. So what we do is we run restricted Delaunay triangulation, which connects the vertices with each other. However, as you can see, we also end up with many triangles that we actually do not want. So what we do is we take the triangle soup that we obtained after 11,000 iterations and we calculate the intersections with all the triangles that we obtained from Delaunay triangulation. And then we simply remove all the triangles that do not have an intersection with our initial triangle soup. And here you can see how we are slowly removing all those triangles, and then we end up with a connected mesh up after just a couple of seconds. However, you can see that the visual quality gets a little bit worse, so we just have to continue the training for another 19,000 iterations to first refine the quality of the mesh, but also to converge towards a fully opaque triangle. So here you can now see how the visual quality gets again much better, and we get a high visual quality. And you can also see on the top right corner that the average triangle is now converging towards a solid, fully opaque triangle. At the end of the training, we then get a high visual quality with connected triangles and fully opaque triangles. And you can, for example, see here in that example that even with tiny or small details, for example, the spokes in the bike, they are still reconstructed, even though we just have fully opaque triangles. Here's another example where you can see that also in this case, the visual quality is extremely nice, even though we just have fully opaque and solid triangles. Also compared to current state of the art, you can see that we have not only a much higher visual quality, but we are also 2 times faster and use 2 times less memory than current state of the art. And the cool thing is that after training, we just train it for 40 minutes, and without any post-processing, you can just put it into a game engine, and you can do all the cool downstream applications, such, for example, physical interaction. You can just throw a ball to the table, and it will bounce back. Also, you can put a character into the scene and just explore it as in a video game and just run around. Also, editing is now super easy. You can just add stuff, you can remove stuff, you can change the position of objects, and pretty much do whatever you want. Or ray tracing is also super easy. You can just put a mirror or glass in the middle of the scene, and then you can see the reflection of the 3D scene in a mirror or in the glass. Another big advantage of MeshSplatting is that each pixel is just, or the color of each pixel is just obtained by a single triangle. So if we want to extract an object, we know that each triangle that colors a pixel inside the mask is actually part of the object. And therefore we can easily extract an object. For example, here we use sand to mask the garden table and flowers, and then we can easily within seconds just extract an object. And we put it into a blender, for example, and just render the RGB object, or just the mesh without colors, or just the normal map of the table. That was MeshSplatting. Thank you very much. We have our poster session at number 14, so make sure to come by. Thank you very much.
Thank you for the nice talk. Are there any questions?